All right, today we're jumping into a full-blown cosmic detective story. We're chasing one of the fastest objects ever found, a pulsar called B1508+55. Now, this thing is a tiny, super-dense star located about 6,800 light-years away in Ursa Minor. And it's moving so ridiculously fast that it basically forced astronomers to go back to the drawing board on how stars can even be launched through space.
And this is the number that started it all. Get this, 1,083 kilometers per second. Using a network of radio telescopes, scientists clocked this pulsar speed directly. And I want to be clear, this isn't some back-of-the-envelope calculation. It's a direct measurement of a speed so high, it's hard to even wrap your head around.
To really put that into perspective, think about this. We feel like we're moving pretty fast as the Earth orbits the sun, right? That's 30 kilometers a second. A rifle bullet is screaming along at about 1 kilometer a second. This pulsar is moving over 1,000 times faster than that bullet. It's so fast, it could cross the entire United States in about 4 seconds. Just gone. So you can see why this immediately created a massive headache for astrophysicists. A speed like this wasn't just impressive, it seemed to shatter the known models for how these things, neutron stars, get going. It felt, for all intents and purposes, like an impossible speed. Which brings us to the big question, right? What kind of insane, cataclysmic event could act as a slingshot powerful enough to launch the dead core of a star at over 2 million miles per hour? Well, it turns out there were two main suspects on the list. Okay, so on one hand, you've got the binary disruption idea. Just picture two stars whipping around each other super fast. One of them goes supernova, and poof, the other one is flung out into space like a stone from a slingshot. Then you have theory number 2, the natal kick. This one suggests the supernova explosion itself was lopsided, giving the brand new pulsar a massive shove in one direction. But here's the problem. When you run the numbers on the binary disruption theory, it hits a hard ceiling. Even in the most perfect, most extreme scenario, that slingshot effect just can't get you past about 700 kilometers per second. And our pulsar is going way, way faster than that. So that theory alone just doesn't cut it. Which leaves us with the natal kick. And the physics behind this is so cool. See, a supernova doesn't always explode in a perfect, beautiful sphere. If the explosion is just a little bit uneven, more energy pushing out one side than the other, the newborn neutron star recoils. Just like a rifle kicks back when you fire it. It is the ultimate cosmic cannon. So, the bottom line is, a powerful natal kick is the only way to explain this speed. It's not optional. Now, it's possible it got a sort of 1-2 punch, maybe a little boost from a binary system plus a huge kick from the supernova. But that kick, it absolutely had to be there. Okay, so we've got our prime suspect for how it was launched. But that just kicks off the next phase of our investigation, finding the scene of the crime. Where in the galaxy did this incredible event even happen? Exactly. A cannonball flying that fast is going to leave a pretty straight trail, right? So if you could just measure its path with enough precision, you could follow that trail all the way back to its starting point. And that is exactly what astronomers set out to do. The whole technique is basically cosmic forensics. First, they used radio telescopes to nail down its current position and motion. Then they figured out its age, about 2.34 million years, by measuring how much its spin is slowing down. And finally, they just hit rewind, tracing its path backwards through time to find its cosmic cradle. And here's the raw data they were working with. The pulsar is thousands of light years away, way high above the main disk of our galaxy, and it's moving almost perfectly away from it. All the evidence screams that this thing is an exile, launched from the star-filled plain of the Milky Way millions of years ago. And when you trace its path back, the trail leads straight to the Cygnus region, which is one of the busiest star factories in our entire galactic neighborhood. So it was born there, got kicked out with unimaginable force, and now it's moving so fast it's never coming back. It's actually going to escape the Milky Way's gravity and just drift in intergalactic space forever. But the story doesn't end there. Just when we thought we had this case all wrapped up, a brand new mystery popped up. As scientists kept listening to the pulsar's radio signals, they noticed something else, something weird in the data that just wasn't supposed to be there. See, the pulsar's super clean rhythmic pulse was being followed by these faint, delayed copies, these ghostly echoes. And as this quote from the research explains, the big idea was that these echoes weren't coming from the pulsar at all.
They were being created somewhere in the supposedly empty space between it and us. The culprit here is something called interstellar scattering. We think of space as empty, but it's not. It's filled with this super thin soup of charged particles. And when the radio waves from the pulsar fly through a cloud of this stuff, the waves get bent and deflected, just a tiny bit.
The concept itself is actually pretty simple. The main signal from the pulsar takes the most direct route to Earth, like a highway. But any signal that gets bent by one of these plasma screens has to travel a slightly longer path. It's taking the scenic route. So it arrives at our telescopes just a fraction of a second later, and we hear that as an echo. Now, by using radio telescopes all over the world as one giant eye, astronomers could actually triangulate where this scattering was happening. And the results was a total shock. The plasma screen causing all the trouble wasn't anywhere near the pulsar. It was incredibly close to us, only about 400 light years away. The pulsar is nearly 20 times farther away than the thing creating its echoes.
But then came the final twist. Later observations using an even more powerful array of telescopes gave them data that just didn't quite fit. The way the signals were changing suggested that a single, simple screen couldn't explain everything they were seeing. No, it looked like there might be at least 2 of these scattering screens layered along our line of sight.
And this is where the whole story just flips on its head. The investigation was no longer just about a fast-moving star. It was about what this star was accidentally letting us see along its journey. We started out chasing this impossible speed, right? But in doing so, we stumbled onto something so much more important. By pure chance, this hyper-fast pulsar has become an invaluable scientific instrument. It's not just an object anymore, it's a probe. So this is its new job. As B1508+55 streaks across the sky, its signal acts like a flashlight moving behind a dusty window. It backlights all these invisible plasma clouds, and those echoes let us map their structure in 3D. It's showing us that the space between stars isn't empty. It's this complex, multi-layered landscape of invisible filaments and sheets. So yeah, what started as a simple question about how fast something can go turned into a whole new way to map our galaxy. By chasing this one cosmic cannonball, we literally found a new way to see the invisible stuff that filled the space between the stars. It really makes you wonder, doesn't it? We set out to solve one mystery and ended up discovering a completely different one that was hiding in plain sight. This one pulsar accidentally unveiled an entire invisible landscape just a few hundred light years from our home. What other incredible secrets are out there, just waiting for the right tool, or maybe just the right cosmic accident to come along and show us?